Welcome back to Honors Calculus. In this video, we're going to continue our discussion of analyzing graphs, finally bringing everything together in graphing functions. Oh, I've gone blurry again. Sorry about that. Anyway, the idea of this video is literally to bring everything together that we've been working with so far. We know how to find the axis intercepts of a function. We know how to identify the extrema. We know how to identify the concavity and points of inflection. We know how to look at symmetry. We know how to look at vertical and horizontal asymptotes. And if we bring all of that together, we should be able to analytically determine enough information about a function in order to sketch the graph without having to rely on software. In today's age where software is readily available, why you need to do this is a little bit more shaky, but it's a good practice and a good way of wrapping up all of the tools of analyzing functions that we've been working on. So let me get my head out of the way and let's dive right into an example. Let's take a look at the graph of the equation y equals x squared plus 3x plus 2 all over x minus 1. Starting with the things that you're familiar with coming into calculus, we can find the domain of this function. Domain is all values for which the function is defined. And in this case, that's going to be x minus 1 cannot equal 0, which means that x itself cannot equal 1. The domain of the function is every value for x except for 1. If we want to write that in interval notation, we could say that the domain, which is usually written as a curly d, is the interval from -infinity to 1, union with the interval from 1 to infinity. We could worry about range, but I'm going to tend to not worry about that. Continuity is always a question. A rational function like this one, we know is continuous everywhere on its domain. We can worry about axis intercepts. The x-intercepts, I want to start with the y-intercept. Right. This is a function, so we know that there's going to be exactly one y-intercept. And y-intercepts always occur when x is equal to 0, which means that y is going to be 0 plus 3 times 0 plus 2 over 0 minus 1, which is -2. So we have the point 0, -2 as one of our intercepts. We can also find the x-intercept. X-intercepts are points where y is equal to 0. So we substitute in y equals 0. And on the left-hand side, we have x squared plus 3x plus 2 over x minus 1. And because I know that x is not equal to 1, because I've already excluded that from my domain, I can multiply both sides of the equation by x minus 1 to get that 0 is x squared plus 3x plus 2. And that factors into x plus 2 times x plus 1. We can split that up using the zero product rule, getting that x is -2 or x is -1. And there are two x-intercepts, -2, 0 and -1, 0. You know from previous mathematics courses that usually speaking, the excluded values, the points that are not in the domain of a rational, result in a vertical asymptote. In this course, we've put that on slightly more solid footing by realizing that we should take the limit. The limit as x goes to 1 of x squared plus 3x plus 2 over x minus 1. And we can factor that numerator into x plus 2 times x plus 1 . But the important thing is that this is going to give me, in this case, it's 5 over 0, which is not the indeterminate form, which means that there will be a vertical asymptote at x equals 1. I'm sorry, I can't do arithmetic. 1 plus 3 plus 2 is 6, not 5. Stupid mistakes. Another interesting question, will there be a horizontal asymptote? There are some rules that you learn in algebra coursework on how to determine if a rational function has a horizontal asymptote or not. Thinking about it in terms of the limit is a little bit more straightforward and doesn't involve any special rules. So we can also look at the limit as x goes to infinity of x squared plus 3x plus 2 over x minus 1. Highest exponent on anything here is the x squared, so divide top and bottom by x squared, and we have the limit as x goes to infinity of 1 plus 3 over x plus 2 over x squared all over 1 over x minus 1 over x squared. Again, highest exponent is the square here, so we multiply top and bottom by x squared. But in doing that, 3 over x tends towards 0. Let's put that the other way so that it's actually visible as something different. That's going to tend towards 0. That's going to tend towards 0. That's going to tend towards 0. And we again end up with a 1 over 0. 1 over 0 is not indeterminate, which means that the limit does not exist. And because the limit at infinity does not exist, there's going to be no horizontal asymptote. We should separately check the limit as x goes to negative infinity because the horizontal asymptote on the left and on the right can be different. But if the limit as x goes to infinity does not exist, the limit as x goes towards negative infinity also will not exist. If it does exist, then we check left and right to make sure that they're the same thing. All right. So far, this has all been things that we could have done without calculus, although calculus makes remembering how they work a little bit easier. We also have some things that we could not have done without calculus, like identifying relative extrema. If we have our function f of x is x squared plus 3x plus 2 over x minus 1, we can take the derivative of this function, which is going to be a lot of fun. Derivative of the numerator will be 2x plus 3 times the denominator minus the numerator times the derivative of the denominator, which is just 1, all over the denominator squared. All right, 2x plus 3 times x minus 1 is going to be 2x squared plus 3x minus 2x minus 3. And then we have minus x squared minus 3x and minus 2. And the denominator I'm keeping factored because my hope is still that I'm going to be able to reduce this fraction before I'm done. All right, combining some like terms, we have 2x squared minus x squared, which is x squared. We have 3x minus 2x minus 3x, which is negative 2x, and we have minus 3 minus 2, which is negative 5. And okay, that doesn't reduce any. So we have the derivative, and we can use the derivative to determine critical values, which are places where the function is either 0 or undefined. F prime is undefined at x equals 1, which is already a place where the function was not defined, so not a surprise there. But that is something that we're going to have to keep in mind as we start checking other things. But we can also check where f prime is equal to 0, and the function is equal to, or the derivative is equal to 0 when its numerator is 0, so that's x squared minus 2x minus 5 is equal to 0. Right, that again doesn't factor, so I guess we jump to the quadratic formula. X is negative b, negative 2 is just 2, plus or minus the square root of b, which is negative 2 squared, that's 4, minus 4 times a, which is 1, times c, which is negative 5. Negative 4 times negative 5 is positive 20, all over 2 times a, which is still 1. Right, square root of 24 does reduce. There's a common factor of 4, which is a perfect square. So this is 2 plus or minus 2 square root of 6 all over 2. And then simplifying that fraction, I get that x is 1 plus or minus the square root of 6. Square root of 6 is somewhere between 2, the square root of 4, and 3, or the square root of 9. Which is good enough for our purposes. So 1 plus square root of 6 is somewhere between 3 and 4, and 1 minus square root of 6 is somewhere between negative 1 and negative 2. All right, so I'm going to sketch out a number line. I'm going to plot 1 minus the square root of 6. I'm going to plot the place where I'm undefined, positive 1, and I'm going to plot 1 plus the square root of 6 as well. But what I really need to do is find some points around those points. Right? 1 minus square root of 6 is somewhere between negative 2 and negative 3, which means that negative 3 is definitely over here to the left. And 0 is somewhere between 1 minus root 6 and 1. Then likewise, 1 plus root 6 is somewhere between 3 and 4. So I could pick either 2 or 3. I'm going to go with 2. And then something bigger would be, say, 4. And if I evaluate f prime at each of those points, right, I can get a numerical value, but the only thing that really matters is, do I get a positive or negative value? See, negative 3 squared is 9. 2 times negative 3 is negative 6, and then minus 5. So we have 9 minus negative 6 minus 5. 9 plus 6 minus 5, which is 10. But again, the only thing that really matters is positive. I can, in the denominator, I have x minus 1 squared, which is always positive. Put in 0, I get -5 over something positive, which is going to be negative. Put in 2, I'll get 4 minus 5, which is negative. And put in +4, I get 16 minus 8, which is 8, minus 5, which is 3. Again, something squared is always positive. So positive divided by positive is positive. Right? If we have increasing and then decreasing, this is going to be a, let's try that with the other pen, maximum. If we have decreasing and then still decreasing, we get really nothing out of that. But again, that's a point where we were undefined anyway. But then we have decreasing followed by increasing, which is what a minimum looks like. We can evaluate the function at these 2 points if we want to. That will give us a couple of extra points to plot. Here is where I'm going to start cheating. I'm going to grab out my calculator and ask my calculator, what is f of 1 plus the square root of 6? Which again was going to be 1 plus root 6 squared plus 3 times 1 plus root 6 plus 2 all over 1 plus root 6 minus 1. And I get that this point is approximately 3.4 and that's going to be 9.9. And then I can also evaluate f at 1 minus the square root of 6, which same thing, just with minuses. And I get that that's negative 1.4 and 0.1. All right, so with that, I have a couple of extra points I can plot. I know that I'm going to have a maximum here. I'm going to have a minimum there. And honestly, with just that, I have enough information to graph the function. I probably should look at points of inflection as well, but I'm going to end it here because this has given me a very good picture of what this function looks like. So I sketch out some coordinate axes. I draw in my vertical asymptote at x equals 1. I put in my zeros at x equals -1 and at x equals -2. I put in my maximum, which is right between those. I put in my minimum, let's see, that's 1, that's 2, that's 3, there's 4, and 10 is very high. So let's actually kill off some of this and move this whole thing down so I can fit a little bit more on the screen. And what you'll notice is that my x-axis is counting every 2 spaces as 1, my y-axis is counting every 1 space as 1, so that I have any hope at all of fitting things in. But I know that I have to have a maximum here, which means I'm going to have a curve that looks kind of something like that before it heads down towards the asymptote. And I have to have a minimum here, which means I have to go towards the asymptote before continuing off in the other direction. And that gives me a decent picture of what the graph of this function is going to look like. Right? There's not really any room for a point of inflection, although I probably should check to make sure that there isn't one by taking the second derivative and setting that equal to 0. It's always possible. In fact, there probably is. These probably at some point over here start trailing that way. This probably starts going kind of that way. Right? It doesn't change direction, but changes its curvature a little bit. Right? But playing around with all of these features, pulling everything together like this, we can figure out what the curve is going to look like without having to resort to using computer software. Again, why would I do this when I could just fire up Desmos and get something that looks a little bit nicer? No, that's really never going to be something useful. But understanding how all of these functions, how all of these features translate into the graph will help you understand how they work and build up how to use them in future courses. So I am going to ask you to consider the function or the graph y equals x squared minus 9 over x. And not using Desmos or anything like it, I would like you to try to analyze this curve by hand. Identify asymptotes, zeros, intercepts, extrema, if you can find them, points of inflection, so on and so on. Sketch the graph by hand without relying on computer software. Once you've finished sketching the graph, you're welcome to fire up Desmos, graph this thing, see if it looks the same. But again, I want you to see how much of this you can figure out just working by hand. See where you can come with that, and I'll see you in the next video.